virtual instrument in the lab view. Now coming towards the experimental results, the harmonic models, the amplitude spectrum that was obtained for different harmonics, for different appliances. This figure shows the current waveform drawn by a laptop when it is running on a AC power. It was done for an Acer laptop. So it is the current waveform for a laptop when it is running on the AC power. You can clearly see that it is not a sinusoidal waveform. It should have been ideally a pure sine waveform, but it is a totally distorted waveform. And if we calculate the total harmonic distortion in the current, it has a higher value of 194%. And then the amplitude spectrum is showing you all different parameters, all different amplitudes of different harmonic models. So, if there is a harmonic distortion, it also has an impact on the power factor. True power factor is defined as the ratio of the actual power to the total apparent power. Whereas the displacement power factor, which we consider more conventionally, it is just the angle between the fundamental voltage and the fundamental current. So, we got about the displacement power factor measured by the power quality meter for the laptop, which was equal to 0.454. However, the true power factor, which in the presence of the harmonics can be calculated like this, we get a distortion power factor in the presence of the harmonic distortion, in which we this equation is based upon the assumption that the total harmonic distortion in the voltage at the time of the measurement was less than 10%, and at the time of the measurement, at the time of the experiment, the total harmonic distortion in the voltage was only 0.03%. So this equation is pretty much applicable to all particular experiments. So by combining, by using that equation, we have got the value of the distortion power factor for the laptop, which is 0.479, and the true power factor is completely equal to 0.217, and we all know that ideally power factor should be equal to 1. But because of the harmonic distortion, we have a very, very low power factor for laptop, which is equal to only 0.217. We repeated the same experiment for all different appliances, including the personal computer, a compact personal lamp, that is an energy saving light, and a fridge, and as well as the microwave oven. So all the parameters, the amplitude spectrum as well as the phase spectrum, including the total harmonic distortion and true power factor, is given in the table. So after obtaining all these harmonic models of different appliances, these were introduced into simulation software, into the harmonic library of simulation software to perform that simulation of a distribution network to find out the total harmonic distortion at the point of common coupling. Point of common coupling, which is usually defined as the point nearest to the utility from which another consumer can be supplied. So in this network, if we look closely, we have got the point of common coupling that we have chosen in this distribution network is bus bar number 4. Also, we perform the harmonic analysis to find out the voltage and the current waveform at bus bar 8, which is the furthest bus bar from the distribution transformer. This whole distribution network, which was simulated, is based upon a practical distribution network based in Pakistan, and the impact has been analyzed for a 100 kVA transformer. The E1 in the figure, which is supplying 18 different homes, and the details of different homes, the hypothetical loading of all these non-linear loads is shown into this particular figure, in which the non-linear appliances are representing 25% of the total load only. So the rest of the 75% load is being modeled as a linear load, which is not creating any harmonic distortion. And as far as the IEEE standard is concerned, 5% is the maximum allowed value in the total harmonic distortion at the point of common coupling, and 3% is the maximum allowed value in the individual harmonic distortion. And if we go to the harmonic distortion in the current, there are a few limits for the harmonic distortion in the current, only for the individual harmonic distortion. There is no particular limit defined in the IEEE standards for a total harmonic distortion in the current. Now this figure shows us the current waveform at a point of common coupling. You see, this current waveform here should have been ideally sinusoidal, but we are getting almost a square waveform because of the presence of the various non-linear home appliances. And if we look closely at that particular table, the 3rd, 5th, 7th, 9th, and 11th harmonic, these are violating the IEEE standard for the individual harmonic distortion in the current. And when this highly distorted current flows through the network, it also distorts the voltage. So there you go. This is the voltage waveform at the point of common coupling. total harmonic distortion at the point of common coupling is 9.43%, which should have been less than 5%. And the third, seventh, and ninth harmonic, these harmonics have the individual harmonic distortion more than the standard values. Now we also create a current waveform at the furthest bus bar, that is at bus bar number 8, in terms of the length of the transmission line. So there you can see that the total harmonic distortion in the current at the furthest bar is 40.68%. So by increasing the distance from the distribution transformer, the system impedance increases. The increase in the system impedance, the total harmonic distortion also increases. Thank you very much for reminding me. And this is the voltage waveform at bus bar 8, and the total harmonic distortion is 14.50, which should have been like less than 5%. We also calculated the distortion power at the point of common coupling. In presence of the conventional loads, we can the power diagram can be represented in a two-axis plane. However, in the presence of the distortion power, in the presence of the harmonic distortion, we need another axis to represent the distortion power, which is shown in the figure on the right hand side. So the distortion power, that equation gives us the distortion power which is flowing in the presence of the non-linear load, and the equation below that gives us the apparent power in the presence of the harmonic distortion. By combining those two equations, we got this particular equation for the total distortion power, and by putting the values found out using the simulation, we found the total distortion power 29.80, and this is just another non-useful wastage of the power from the system, just like the reactive power mostly. So if we calculate the total power factor at the point of common coupling, it is also deteriorated from 0.91 to 0.86 because of the total harmonic distortion. Then you can easily see that higher the value of the harmonic distortion, lower will be the value of the distortion power factor. So what we want is that we want a higher value of the power factor. But with the increasing harmonic distortion, we get a decreasing value of the power factor, which is also another impact of the harmonic distortion onto the network. By having a lower value of the power factor, the system efficiency also decreases. By coming to the conclusions, the results show us that the individual harmonic distortion as well as the total harmonic distortion in the voltage as well as current at the point of common coupling and the consumer is like way beyond the acceptable standard limits. And the other conclusion that was like mentioned over here is that with the increasing distance from the distribution transformer, the harmonic distortion increases. And with the harmonic distortion, the distortion power in the system increases. Also, the power factor becomes deviated, and also the situation will become even more critical with the emergence of the newer technologies at the massive scale of the distributed generation and the electric curves into the system. So steps are required to mitigate the harmonic currents. And thank you very much. Any questions?
My question is, for me, the most important is not the amount level, but the level of penetration. How much my distorted rod, what is the percent of the rod from comparative to the system? So, for your opinion, what is the limit for me to have, for example, I have 40% of distortion and my load is 1 kilowatt. And I have 10% of harmonic, and my load is 1 mega. What is your opinion?
Well, let me rephrase your question. Like, if I am right or not, please correct me. You are asking me what should be the limit upon the total non-linear loads which we can insert into the system?
Right.
Well, there is no limit. We cannot put a limit upon a consumer. Like, if I am a consumer, I am buying electricity from a utility company. They cannot ask me to not to use a computer, to not to use a laptop, to not to use the energy saving light. I can use anything in my home. But what I can do is that instead of putting a limitation upon my user, what I can do is that I can put a penalty upon him that you need to buy a filter from us as well. You will need to put the filter in your home if the total harmonic distortion is above 5% in your home. So in this way we can put the limit on the consumer. Okay, in this way we will discourage the use of the non-linear loads. But the thing is this, in the future all the loads are non-linear now. Even like we are talking about the smart grids. In the smart grids, we are talking about the smart devices. And when we are talking about the smart devices mean like which are electronically controlled. So whenever a device is electronically controlled, we cannot eliminate the harmonic distortion. So we need to re-evaluate the standards and all the aspects of all this before stepping into a greener future. I hope that answers the question.
Okay, thank you very much. So I think we need to move to the next speaker. Thank you very much. So, Mr. Da Silva from the Instituto Federal de Educación.